So as we have mentioned earlier, we have a leaf procedure, leaf function or a procedure. This is the function that is not calling itself nor calling other function. We have also mentioned that example that in this basically code, we have G, H, I, and J. All of these by default will be saved in my argument registers. Since I have only 4 registers, so basically A0, A1, A2, A3, and this will be the maximum number of arguments we would basically cover here. And then you have integer f, and I'm giving you here an information that f is basically saved in S0, so this will be given to you. And this f is not but G plus H minus I plus J, since this is A0, A1, A2, A3. So basically I am adding A2 plus A3, and I'm also adding A0 plus A1, and the results from there is basically subtracted from each other. So if this is in a certain temporary register and this is in another temporary registers, and then do this subtraction, and then the results will be in F. And after I have the results in F or in S0, I have to make sure that my results are basically in V0. By default, the results will be written in V0, and the arguments will be saved in the argument register. So these information I don't have to give you, but I need to give you where is F. If I didn't, you can just assume whatever F is saved in a certain registers and just continue all of your solution according to your assumption. One of the most important things we have highlighted regarding this code, that before I dive in to implement the function, first of all, I have to make sure to save all of the information that is saved in a saved register. Why is that? Because actually this is the rule of the MIPS. A rule of thumb in the MIPS, that you have a certain particular code, for instance, and then you have your function. When you have your function, you will go inside your function, implement all of the codes, and then return back to your original code. So let's say that I'm using here in my code for at some place, I am using S0, but also I am using S0 here. So that means that if I have S0 here and I already used it there and then return it back to that code is no longer reserving that S0, yet instead having this S0. And this is an issue. With the MIPS register, this is an issue. The rule that as soon as you have anything saved in the S, please, before beginning to play with it, save this guy in a safe place, secured place, then do whatever you would like with S0, and at the very end here, after you finish, please retrieve this back to my code or to my register or to whatever the place is. So now I have my S0 in my register as it was here. Does that mean that if I have a T0 or T1 or any temporary registers, I have to do the same? You don't have to. You can do, but you don't have to. If I explicitly ask you to write an optimized code, MIPS optimized code, of course, you don't have to do that with temporary registers. If I didn't mention, that's fine. You can do that. It's just you are writing more lines. But when you need to do that with saved registers, anything that S0, S1, S2, and so on, designed by S, has to be basically dealt with like that. And because of this, before I begin my function, do whatever I would like, I have first to save my S0 in a safe place, do my function, and then return it back. How we can do this? This is my stack. Stack pointer is always pointing out to the very first part of my memory. I knew now that I would like to save basically S0. So I have to reserve the spot inside my memory before beginning the movement. It's exactly the same thing, but if you would like to use the stuff that is on my desk and save it in a secured place, before you begin to move the stuff, you have to make sure that there is an empty, reserved, secured place in a storage unit, and then you will begin the movement. That's why I have to move my stack pointer 4 blocks down. So 1, 2, 3, 4. Now here my stack pointer. So that means that basically this place 1, 2, 3, 4 is ready for any information to be saved in. In that case, of course, after I move the stack pointer here, now I can move easily store S0 to this particular place from my register. So please move it here. At the very end, after I have my function, what I need to do is the other way around. Move back S0 to here. So move it back to here. How? By load word. And then move my stack pointer up, which is exactly the same thing also when you deal with a storage unit. Before you tell the storage unit guys there that you no longer need the space, you will actually move your stuff back. Yes, you take your stuff out of that storage unit, and then you will tell them, please, I am no longer in need of that particular place. Here is exactly the same. Move by load word S0 from stack pointer to S0, and then move up my stack pointer again by 4. So it was -4 and then +4. Then I'm doing the function. The function here it should be easy because, as we mentioned, we are adding this by this, putting this in a temp register, this by this, putting that in a temp register, and then subtract the results, putting this in S0. And after I have it in S0, I have actually to copy this in V0. That's all. One more rule of thumb, if you recall, this is my code, and then my function, and then my code. The problem that when I enter this function, there is a question mark here that after I finish my function, where I should go. What is the next address I should execute? There is a question here. We mentioned that as soon as I finish this line and I'm calling my function, I am using something called jump and link. Jump and link means I will jump to my function, but I will link the end of the function to the next the address of the next instruction to be executed. How? I will basically save this value in one of my register slots called RA. So that will be saved here. As soon as you finish, you will go and open that RA and check what is the address that is written there. As soon as you know that address, you will be able to return back to here. It's exactly the same thing if you would park your car in a certain place. And then you want to do shopping, yes? But your park is in a certain particular location or number or park number or there's something. But unfortunately, you don't have a good memory, so you have to write down that my park is in that and that and that. After you finish shopping, you just need to open your note again and see like where I parked my car, and then you will go to that particular place. Here is exactly the same thing. We are following the same structure that we would think of in our normal life. And then that's why I have here jump register to return address. So I know now that I have actually to return address my code, because this function is a part of course, a bigger code. So this was for the leaf procedure. For the non-leaf procedure, it's basically a function that can call itself or it can call another function. And that's why it's called non-leaf procedure or non-leaf function. So it can be that way. And of course, you need to save again any saved registers, but in some cases, you actually need to save the arguments. Why? Because if you are inside a function and then you are calling another function, or you are calling the function itself, you have to assure that you're still saving the track of the arguments. Let's say I have the first function has arguments A, B, C, D, for instance. So A will be saved in A0, B will be saved in A1, then C in A2, and so on. However, the second function is using argument C, comma D. But in that second function, the A0 will be C, the A1 will be D. So if I didn't keep a track of all of these arguments, I would actually switch between the A and B and the C and D. So we have to be clear in that regard. That's why it is extremely important, especially with the non-leaf procedure, to keep track with the arguments register inside my procedure. One other also important thing that when a non-leaf procedure, I need to save also the return address, because again, it might differ between like the first place to return and the second place to return and so on and so forth, since the function is calling either itself or it's calling another function. And I want that return address to be inside the function, not the return address of the main code. Correct? Because of that, I have to save it in the secured place, the same example as we mentioned with the stuff that you need to save before using others like person's disk or whatever you would like to use. So let's take that example. I have a higher level code here. And then fact, int n. So this is my argument. I know by default that this is an A0. I don't need to give you this information. And then fact is basically referred to factorial. In that code, it says that if n is less than 1, please return 1, else return n multiplied by factorial n minus 1. Also, as we mentioned that by default n will be in A0 and the results by default will be saved in V0. So I don't have actually to give you this information. Unless I said like the results in V1, you have to make sure that actually you save the results in V1, not in V0 and so on and so forth. So we need to implement that in as a MIPS code. Before I went inside the function and think like how I would implement the function, the very first thing that I need to take into consideration is what exactly I need to save from my registers before I begin to play with. Since this is non-leaf, I have to go just like roughly quickly inside my code and see like if I have to save the argument registers or not. Most probably yes. And I need to save my return address register. So that means in this case, I basically have to save in my stack pointer two stuff. So the stack pointer was here, but I know now that I need to save the argument A0 and I need to save the return address register. And because of that, each of these registers is 32 bits. This is 32 bits. So if it is 32 bits, I actually need 4 slots inside my memory, another 4 slots inside my memory, and then I will begin the movement. But before I begin the movement, I have to tell the stack that I would like to reserve a place inside you. How I can do that? Before this movement, I have to move the stack pointer. This is the stack pointer. I have to move this down by 8, minus 8. So this will be my new stack pointer. Why minus 8? Because this will take 4 slots. This will take 4 slots. So basically, I need 8 slots. Move my stack pointer here. After that, move this to here, move this to here, or the other way around. This is just the rule of thumb before I do anything with my function. And this is exactly what we basically need to think on. And then I will begin to think about, okay, how I can call my function and how to restore the value from the stack. So again, here, this is the function. that basically written in MIPS. Just to remind you, if n is less than 1, return 1, else return n multiplied by factorial n minus 1. And we will go over these steps now. First of all, as I mentioned at the very beginning, stack pointer move by 8, and that's why here minus 8. Please store word the return address register in this location. Please store word the A0 in that particular location. So now I have in my stack pointer these two stuff here. Then what I should do? I need to begin to implement my function. I need to check if n is less than 1 or not. This is the very first step. How to check if n is less than 1 or not? In MIPS, I have set less than. But since this is constant, so I have to use immediate. So set less than immediate. So I would like to check if a node is less than 1 or not. If I would like to check something like that, then I have two options. It is either less or greater. But since this is factorial, so I know in advance, in order to calculate the factorial, I would begin first with the bigger number. Yes, factorial 5 is 5 multiplied by 4 multiplied by 3 multiplied by 2 and so on and so forth. So I would expect that the very beginning n would be like larger than 1, unless just the very first I'm telling you like calculate factorial number that is less than 1, but this is not usually the case. So I need to check if it is less than 1. If it is less than 1, basically if it is true, t0 will be equal to 1. If it is not true, t0 will be equal to 0. At the very beginning, I expect, of course, that if this is not true, I am expecting that t0, that n is not less than 1. And accordingly, what I will get is t0 equal to 0. But I would like to double check if t0 equal to 0 or not. So I can go to this path or I can go to this path. That's why we have here the second check, branch equal. If t0 equal to 0, please go to L1. Where is L1? L1 is that address. If it is not, please go to the next instruction in your code to be executed. Of course, if we begin with n equal to 5, for instance, of course, when I do this check, it is not less than 1. And accordingly, t0 will be equal to 0. So branch equal to 0 is equal to 0, correct? Then please go to L1. So I'm going now to L1. What I should do when I go to L1, I need basically to implement my code here. Because I mentioned if it is less than 1, return 1. Otherwise, do n factorial n minus 1. So what I'm expecting here, that to do the n factorial n minus 1. How I can implement that in the MIPS? In order to implement that, I know that I have n, and I know that I need to call my function factorial n minus 1. Okay, so if I would like to call a function factorial, you told us that just I need jump and link and then write factorial. So I will go here to L1 and then write jump and link factorial. But unfortunately, if I am doing that, jump and link factorial, when factorial look at its argument, it will find that its argument is basically n. But here I have n minus 1. So that means that I have to force this n to be decreased by 1 before I pass it to the function. And because of that, the very first step, I have to add immediate A0 minus 1, put the results or update my A0. So whatever I have now in my A0 is basically n minus 1. So when I'm calling the factorial, jump and link factorial, it is implicitly I am calling factorial of n minus 1. But now the problem that my A0 is holding n minus 1 and is no longer holding n. So how I can get this n to multiply by factorial n minus 1? How I can do that? Unfortunately, I have already overwritten my A0 by n minus 1. So how I can do that? Interestingly, that before I went through my function, if you recall, I have saved my stuff inside my stack. And since I have saved my stuff inside my stack, I have saved the very last n before I have subtracted. And because of that, retrieving the data that is here back to my register will solve this issue. And that's why I have here load word, whatever it was in that location, which was here, if you recall, load it back to A0, do the same with return address, move back my stack pointer up. So no longer I need that. My stack pointer is again here. If this is the case, my A0 has been overwritten again to n. So it was n minus 1. After doing that, I have overwrite A0 by n. Then what I need to do is not but do this multiplication. N multiplied by factorial n minus 1. Factorial n minus 1, that results in V0. N, that results in A0. So A0 multiplied by V0, please update V0. Now you finished your function. You finished like the first part, then jump register to the return address. Then you will go again to your address of your function. So this is one path. You will still do that same things for 3, 2, 1, and then less than 1. While you're going for the last one, you will check set less than immediate. Is A0 is less than 1 or not? At that case, it will be true. And because it is true, T0 will be equal to 1. And when T0 is equal to 1, when you do branch equal, T0 equal to 0 or not, unfortunately, it is not equal. And because it is not equal, I am no longer going to L1. Accordingly, what I need to do is just going to the next instruction to be executed. What is the next instruction to be executed is here. But I know what I should do because it asked me here that if it is less than 1, please return 1. Return 1 means write 1 in V0 because this is the results, correct? So in the results, I have to force V0 to be 1, and that's why I'm adding 0 inside my register. Plus 1, I will put the results in V0. And after I put the results in V0, I no longer need whatever was in my stack and then moved my stack pointer up there, and then jump register, return address, and that's it. But the question here that you might ask yourself, for instance, that in this particular case, when I moved back the stack pointer up by 8, or when I told the guy that is responsible for the storage unit that I no longer need that storage unit, I dealt with this process in 2 different ways. Here, I just told this guy there that I no longer need the stuff. But here, before I'm telling that I no longer need the stuff, I moved my stuff first to my register. So why here I didn't move? Why here I moved? So basically in this case, of course, I have to retrieve the stuff back since I am still calculating the factorial. So each time I have to save back my previous n. However, in this case, this is basically the very last step. And since it is the very last step, you no longer need these information. You already have it. And then just move the stack pointer up. So inside my stack, so the frame pointer will point out to the stack and the stack pointer as well. However, with the stack pointer, as soon as I begin to save some stuff in my stack, my stack pointer is moving basically with the stuff that I am saving. When I wipe them away, basically the stack pointer is moving up again. So the stack pointer is changing according to the data that's saved in my stack. However, the frame pointer is basically always pointing out to the very first high address of my stack. To look closely in my memory, so this is basically my memory. In the memory, I'm saving some of these stuff. The very first thing is basically the stack. Then I am saving something called the dynamic data, or you can refer to that as the heap. Something similar to new in C++ or Java, or memory allocation in C and stuff like that. After that, inside the memory, you save also something called static data, which is saving all of the global variables, for instance, in your code. Then you have the text. You can save, as an example, your code. And then you have some reserved stuff inside your memory. So inside your memory, you have all of these things. By the way, all of this number, I'm not expecting that you will remember it, just for your reference. You know that there is a stack, there is heap, there is static data, text, and so on and so forth. If needs any of these numbers, of course, it will be given to you, and then we can ask. One other operation that we are interested in is the byte operations. Whatever we have mentioned so far, that if you have the memory here, the memory is basically, if you recall, this is 8 bits. If I would like to move a word from my memory to my register, so this is 32 bits. So basically, I'm moving all of these 4 to one of the slots here by load word. I can do the same process back by store word. But the question is, how about if I just need to move one of these bytes only? One, or this one, or this one, or whatever the one that I need to move. Which basically syntax, or which code, or which instruction I should use? We are giving you a new one here that's called load byte, RT, and then comma a certain address. If you recall, load word also RT, and then a certain address. Instead of load word, we have load byte. What does that mean, load byte? Load byte means that if you have the memory here, and you have the register here, and you would like to move that byte, for instance, it is placed in the rightmost 8-bit register. So this 8 will be copied to the rightmost 8-bit registers here by using load byte, or load byte unsigned. You will specify the same things as the load word. You can give the certain address, shift, it can be shift by 1, 2, 3, 4, whatever the shift is, in order to take a certain particular byte. You can do the other way around by store byte from the register to my memory. Since now we knew like how we can deal with the bytes, so let's try to see that example. So with this higher level code, it's telling you like void string copy, and then character X, character Y, and then integer Y, I equal to 0, while this condition, please increment. Soon as this condition is satisfied, please increment I, otherwise, of course, exit the loop. By default, this will be in A0, and this will be in A1. So I don't have to give you this information. What I need to give you is I is in S0. This is the information that I need to give you, that I is in S0. Okay, that's fine. We need to highlight a couple of things here. First, that when I said A0 is holding the array X, that implicitly means that A0 is pointing out or holding the address of the very first element of X. This guy holding the address of very first element of Y. So basically A0 is pointing out to the very first element of X. A1 is pointing out to the very first element of Y. The other important thing that we need to highlight here is the character. If you recall, in all of the examples that we have covered so far, here I always have integer. But this is my first time to have a character. How this will make a difference in my MIPS code. So of course, since I'm using a character here, we already knew that character can be saved in 1 byte, while the integers, we dealt with it as saving in 32 bits. So now if I would like to move any of the stuff from the memory to the register or vice versa, instead of load word, store word, I have to use, of course, load byte and store byte. So as you can see from this code, that x of I will be equal to yi until y of I is equal to 0, I have to exit the loop. So if, for instance, if this is my memory, I have here as an example yi, and of course it is yi, so this means that this is y0, and then my next element in y, y1, y2, and so on and so forth. And I have, let's say, assuming that my x of 0 is here, then x of 1 will be here, x of 2 will be the next, and so on and so forth. So what that said is, please copy whatever you have in y to x. So copy whatever you have in y of 0 to x of 0, y of 1 to x of 1, soon as just to check if y is equal to 0 or not. If it is equal, please exit the loop. So this is basically as easy as that. I just would like to do this copy. But unfortunately, because I'm dealing with a RISC processor, I can't do that at the customer side. I can't do that at the memory side. I have to bring everything back to my place, do the arithmetic operation, and after I finish, I can return back the stuff to the customer. Bring back all of the things from the memory if needed, do whatever I would like, and then return it to the memory. So that gives me an indication that in order to do this stuff, I have to think in a smart way on the process that I need to follow to do something like that. How we would think on something like that. Let's see here how we will do that. But I will introduce it again here, so you will follow the steps easily. So again, I have my memory. Let's say that this is y of 0, this is y of 1, and so on and so forth. And then this is my x0, x1, and so on and so forth. In order to copy this to here, first, I need basically to copy this to my register and then think about what will be the next step. So the very first step that I have here, my register. I will basically copy this here to a certain particular register. And then after I copied here, then I will go and overwrite my X. Correct? This is what I need to do. But in order to do this process, I need to think about all of the details. And this is basically the assembly, that you are doing this in a bit by bit steps, minor or macro steps. The very first thing that you need to ask yourself, okay, I know that I will move this to here, but first, where is actually Y0 in my memory? Where is the address of the very first house here that I have to bring the stuff from to copy it to here? Second question is, where is my X? So after I have my stuff here, I should copy it to a certain particular place. Where is that address? Correct? If you recall, we just mentioned here that A0 is holding the address of X of 0, or the very first array in X. Yes? And A of 1 is holding the very first array of Y0. So that's why I know now that Y0 actually is in A0, and X0, the address, I mean, not the value, the address of X0 in A1, in A0, and the address of Y0 is in A1. Okay. Again, since this is a function, before doing anything inside my function, I know now that I is in S0. Since this is my code and I have a function. Since I is in S0, so inside my function, I will begin to play with S0. And since I will begin to play with S0, so this means that I will override the S0 that it was there in that code. That's why the very first step is basically to save this S0 in my stack pointer or in my stack. And in order to do that, please move your stack pointer by 4, store word the S0 in my stack. At the very end, after you finish everything, you will just return back the S0 as exactly as it was. Move it back from stack pointer to the register. Please move the stack pointer up by 4 and then finish the function, go to return address. So this and this is something that you can write at the very beginning of your function as an example. Then I need to think about, okay, what will be the steps that I need to do in order to get like this here and then copy this in at X of 0. First of all, I need to know where is the address of A of 0. So the address, of course, of A of 0, this is the address of Y of 0. The address of Y of 0 is written basically in a certain argument register here is A1. So I know now that A1 is pointing out to that particular address. Okay. Also, I know from that code that at the very beginning, I need to initialize I to 0. So at the very beginning, I have to initialize I to 0. How? Add 0 plus 0, put the results in S0. Why S0? Because this is what saved my I. So now it is S0 equal to 0, meaning I is equal to 0. Okay, the second thing that I know that my A1 is pointing out to the address of Y0, as you can see from here. Okay, that's fine. What I need to do just to deal with the temporary register instead of my argument, I will just copy whatever I have in my A1 to a register T1. But why I need to do that? Because you would like always to save in A1 the address of the very first element in the array Y. Why is that? Because you would like to have another temporary register, as an example, called T1 that will always point out to the next address of the elements. Meaning T1 will point at the very beginning, will point out to Y0. Then it will point out to Y1. Then it will point out to Y2. Then it will point out to Y3. While the argument is always pointing out to the first element. That's why you need actually 2 registers. And to do that, you have always to update T1 with the value that is, or that was in A1 plus the value of I. Why the value of I? Let me ask you an important question. What is the address of Y of 0? Let's say that the address of Y of 0 is 200 as an example. So this means that this is 200. If I'm asking you what is the address of Y of 1, you know that this is just the next byte, correct? If you know that this is just the next byte and you are just counting by 1 inside this memory, so actually the address of Y1 will be 200. plus 1. What is the address of y of 2? It's 200 plus 2, and so on and so forth. So if the address was here 200, of course this guy will be 201, then 202, and so on. And that's why at the very beginning I'm adding the A1 plus the S0. The very first value of S0 is 0. So now T1 is also pointing out to the very first address. Okay, if this is pointing out to the very first address, so T1 now is holding the address of YI. What is next? Next, I know exactly where is the address of YI. Yes. As soon as I know where is exactly the address of YI, I can easily say, please load byte unsigned from that particular address to a certain register called T2. So I'm pointing out to here, I'm telling you, please go and bring whatever is there inside address 200 and copy here into T2. So now I have actually the actual value of my YI, not the address of my YI. Because this 200, which was here, which has been also copied here at the very beginning, which is pointing to the very first, is just holding the address 200. But what is exactly in YI, in Y of 0, that I would like to copy to X of 0, I don't know this information yet. I don't know what is that value. I just know where it is, but I don't know that value. So in order to know that value and to copy it here, I need to say, like, please go to that address, retrieve or load word this particular element, copy to T2, as you can see from here. So it is basically load byte. So now you have loaded basically Y0 to T2. Now I have it here. What I should do? Overwrite X of 0. Correct? Because this is what we said, while X phi equal Y of I. So that means that I will overwrite X of 0 with Y of 0. But in order to do that, I have first to know where is the address of X of 0. We'll do the same exact steps. Where is X of 0? X of 0 is basically in A0. But I need to have another temporary register that will always increment my very first address to know where is X of 1, X of 2, X of 3, and so on and so forth. And that's why I have here T3. Then, after I knew the address of X of 0, X of 1, and so on, each time, of course, in my loop, assuming right now that I am at the X of 0, I know the address that X of 0 is T3. T3, as an example, is here. I know now the address of X of 0, and let's say it was written here in A of 0. Let's say that it was 400. So at the very, very beginning, this had the address of X of 0 or X of I. At the very beginning, it is 400. So it is pointing out to that particular place. If it is pointing out to that particular place, what I need to do is what? I need to copy this Y of I or Y of 0 at that time to X of 0. How I can do that? By store byte. Store byte T2, which is holding the value of Y. Store byte T2, where? To that particular address X, which is in T3, like that. So now I have copied Xi equal to Yi. Then the next step after I'm doing that, I would like to check if Yi is equal to 0 or not. If the Y that I have here is equal to 0 or not. So I have to check if T2 is equal to 0 or not, to check if this is equal to 0 or not. If it is equal to 0, then please finish, exit the loop. How I will finish? I will return my stack pointer, return the stuff back to the register, and then jump register, return address. So I'm just exiting my function. But if it is not If I would check that this is equal to 0, it is not equal to 0. What I need to do, just go to the next instruction to be executed, which is basically here. If it is not equal to 0, please increment the I by 1. Whatever I have here is just increment my I. My I here is S0, if you remember, incremented by 1. So it will be I equal to I plus 1. And after you do that, please loop, jump L1, so loop again to L1. So if you recall, in an I-type format, we have opcode and then RS and then RT and then constant. In that constants, I have 16 bits. So this means the maximum amount of bits that I could use for a constant to be copied in a register is basically 16 bits. This is the maximum that I can hold a constant, correct? The question is, what if I have a constant that is actually 32 bits? Instead of 16, it is the double. It is 32 bits. What I should do in this situation? What the trick that I need to follow in order to copy a 32 bits register? Here is the trick. First of all, I would like to reintroduce again what I have mentioned earlier, that load upper immediate. Load upper immediate RT comma constants means I'm copying this 16-bit constant to the left 16 bits of my register. This is 32 bits, of course. So I'm copying that to the left 16 bits of my register. Let's say RT, as RT can be S0, can be S1, can be T0, can be anything. Okay, let's go a little bit more depth, going depth in that. Assuming that you would like to load a 32-bit constant into register S0, and that constant is basically here. Forget about the yellow and assuming that this is a one constant. And I am telling you that this constant I would like to copy in register S0. How you can do that? You have a number, very big number, very large number. Please copy that to S0. Unfortunately, you have to use I-type, because we mentioned as soon as we are dealing with a constant, you have to use an I-type. But there is a limitation that my I-type, I have only 16 bits. How to solve this dilemma? The trick is here. So you have this constant. When you have this constant, split it into 16 bits left and 16 bits right. When you go to the 16 bits left and read that number, you will find in this particular example that is 61. The left 16 bits, if you read them alone, it is 61. So you will say, okay, load upper immediate to register S0, the 61. So inside my S0, I will go and copy here my 61. When you do this load upper immediate, by the way, you are just clears all the right bits to 0. So this means that all of these just will be zeros. So your S0 has only 16 bits to the left, which I will copy the value of 61. Okay, so that's great. But I know that actually my constants still have a values here, which I didn't use it yet. How I can solve this issue? That's very easy, because I know that all of this is zeros in my S0. If I read the 16 bits number alone, I will find that this is the constant. If I basically OR that constant 2304 with whatever I have in S0, so it's basically ORing that with these zeros. If you OR this 1001, you will find that you have the number. So that's why you have copied actually the whole number. So again, you have a certain particular number. Let's say like you would like to load upper immediate T0, 255. So we have actually the 255 here. You have copied here to T0, and that's all. There is no problem. The question, what if this is a very large number? And this large number, you cannot write in 16 bits. How you solve this issue? If you would like to follow the same exact things, so now you have a very large number, this large number. You will do a step-by-step calculations. You will split this to 16 bits to the left in your mind, just in your mind, in the calculation apart from MIPS. You have the 16 bits to the left, you have 16 bits to the right. You will read what you have here in the 16 bits to the left. In this case, you have 61 in decimal. So you will write load upper immediate 61 to S0. So you have copied 61 to S0. If you have copied 61 to S0, it is the same thing as putting this upper 16 bits to the left upper 16 bits of S0. So you are basically taking this here. Then the next question is how I would move these 16 bits to the right. How I will move it? You know that this number, if you read it by yourself, it is 2304. So what you need to do is just or immediate 2304 with S0, update the S0. If you do that, you are just copying here the least 16 bits, which was here 2304. Keep into consideration that 2304 by itself can be written in 16 bits. 61 by itself, it can be written in a 16 bits. But that whole number has to be written in 32 bits. And by applying this trick, you can actually save a constant that is larger than 16 bits into a register that is 32 bits. There is also another thing that we need to cover, which is the J type. If you recall, we have already explained the R type and the I type. We are explaining now the J type. The R type, if you recall, it was opcode, RS, RT, RD, shift amount, and then function. With the I type, we have opcode, RS, RT, and then constant. With the jump, it's just like you need the jump and then address, correct? Because you say, I would like to jump to an address. If you look at this, what exactly you need as a format to implement something like that? You just need something to tell you that this is jump, and you need another thing to tell you like where is the address, and that's why this is all what we need. Opcode is 6 bits as usual, and then all the rest 26 bits is for an address. And if this is the case, this should give you an indication, a very important indication, that now with the jump, since I can hold 26-bit address, so that means I can jump far away. So if my code, as an example, is 3 million lines, as an example, so I can easily represent that in 26 bits. But with the branch is using I type, which is using only 16 bits. So the maximum that I can use is actually 2 to the power of 16. Yes, to jump to or to branch to. So that means if my code, I would like to branch to a place that is very far away from my place, the maximum that I can get is 2 to the power of 16, correct? Minus 1. Yeah. But with the jump, I can actually hold a bigger address. This gives me an implicitly indication that with the jump, I can go to a far further place than I can do with the branch.